Lesson 1, exponential functions. So an exponential function is a function that has an x as the exponent. So all of these have x in for exponents, and we're going to type numbers into our calculator so that we can figure out what kind of shape this would make. So we're going to type y equals, so 10 to the power of negative 3, and you should get 0.01. If you type in 10 to the power of negative 2, you get 0.01. And the reason why you get that is if you have 10 to the power of negative 3, we don't put exponents in the top. We would have to move it to the bottom. So this would be 1 over 10 to the power of 3, which is 1 over 1,000, which is 0.01. So that's why exponents do that, why they make decimals like that. So I want you to pause the video, and I want you to fill out the rest of the chart for 10 to the power of x. So you should get 0.1, 1, 10, 100, and 1,000. And if we were to graph this, at negative 3 it'd be 0.01, 001, why did I miss a 0? That is going to be really, really close to the line, pretty much on it for our graph because we're going up by hundreds. Same with negative 2. Same with negative 1. For 100, we're going through 1. Let's pretend that's just a little bit up. For 1, we're going through 10. For 2, we're going through 100, finally getting to move. And 3, we're going through 1,000. So all of a sudden, we're all the way up here. It got big quick. So this is what an exponential function looks like. It hugs the x-axis because it gets littler and littler and smaller all the way to infinity. But it will never touch the x-axis. On the other end, it gets exponentially bigger. So we're going to do the next one. So what you're going to type in is 2 times 5 to the power of negative 3. So what I want you to do is pause the video and fill out that chart. So you should get 0.016, 0.08, 0.4, 2, 10, 50, and 250. So if we were to graph this, at negative 3, it'd be really close to the line. At negative 2, it'd be a little bit bigger. At negative 1, it'd still be a little bit bigger. At 0, it's going to go through 2. At 1, it's going to go through 10. At 2, it's going to go through 50. And at 4, it's going to go through 250. And I mean 3. So this is what your graph looks like. Except going through that point. So once again, it starts off really small and gets really big. We call these both increasing functions. Okay, now we'll do our next question. So we have y is equal to 1/2 to the power of x. So you would type in 0.5 to the power of negative 3, and you should get 8. So when you pause the video, fill in all the values. Alright, so we have 8, 4, 2, 1, 0.5, 0.25, 0.125. So this one's a little bit different. We're starting big at negative 3. Starting bigger at 8. Negative 2 is 4. Negative 1 is 2. 0 is 1. 1 is 0.5. 2 is 0.25. 3 is 0.125. So this is our exponential function. And this one decreases. And the reason why it decreases is because our base, that's what we call our number inside the brackets there, the base is 1/2. So if if we have 1/2 to the power of -3, we would have to do the reciprocal to make it positive. So it would actually be 2/1 to the power of 3, which is 2 to the power of 3, which is 8. So really you start off big because you have to do a reciprocal of the fraction first. Okay, and for the last one we're going to do 8 times 0.25 to the power of -3. You can also use the ABC function to do these fractions, and then you do yx to the power of -3. So type the first one into your calculator and you should get 512. Oops. So I want you to pause the video and figure out all the rest of the numbers. So you had 128, 32, 8, 2, 0.5, and 0.125. So we're starting up at 512 for -3. -2 is 128, drops really quick. -1 is 32. 1 is at 2. 2 is at 0.5. 0.25. It's really close. I can't draw that on here. So once again, this is decreasing. Alright, so when we have the function y equals a times b to the power of x, things that are important. Our b value determines if it increases or it decreases. Our a value is also important too. And the reason why it's important is if you look at all of these table of values, another important information we often use to graph is our intercepts. So if we were to find our y-intercept, we would make x equal to 0. And x is equal to 0 here, 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 and here. And if you notice, this would be our a value for each of these. And if there's nothing there, that's the same as 1. So our a value determines our y-intercept, and our b value determines if it is an increasing or a decreasing function. So for this table at the bottom, our a value is 1, our b value is 10. Our a value is 2, our b value is 5. Our a value is 1, our b value is 0.5, and our a value is 8, and our b value is 0.25. For the first one, we know that a has to be greater than 0. For all of the ones that we will do in this class, a will be greater than 0. B also has to be greater than 0, but they're not exactly the same. For the first one, B is greater than 1. So not only is it bigger than 0, but it's also bigger than 1. And because it's bigger than 1, it's an increasing function. For the second one, B is greater than 1. So this is also an increasing function. For the third one, b is not greater than 1. It is less than 1, but is bigger than 0, so we write 0 is bigger than b, which is bigger than 1. And by bigger, I mean less than. I don't know why I put that. 0 is less than b, which is less than 1. And that means that it's a decreasing function. If it's a decimal, it is a decreasing function. A decimal less than 0. So 0 is less than b, less than 1. This is decreasing. And our y-intercept will be our a value. Alright, example 2. We want to show from the table of values that the function is exponential. So the way that we do it is we take our biggest number, and we're going to divide it by the number right in front of it. So if we take 40 divided by 20, we get 2. And then we do the same thing. 20 divided by 10 is 2. Then we go 10 divided by 5 is 2. 5 divided by 2.5 is 2. Now we're at 2.5 divided by 1.25, and you get 2. And the last one is 1.25 divided by 0.625, which is also 2. So when you get them to be all the same, therefore you know that it's exponential, and this is your base. So our base is equal to 2. We also know that since when x is 0, y is 5, that is our y-intercept, so a is equal to 5. So if we wanted to determine an equation from this, it would be y equals 5 for a, 2 for b, to the power of x. So that is the equation for this table of values. And for our last example, we want to determine the x-intercepts, the y-intercepts, the end behavior, domain, range, number of turning points, and if it's increasing or decreasing. Alright, so for the first one, there's no x-intercepts. There will never be x-intercepts because you can't cross the x-axis. It's always going to be above for right now. Our y-intercept is at 2. It crosses the y-axis at 2. Our end behavior is that it starts in quadrant 2 and it goes to quadrant 1. This is the same as the other one. It starts in quadrant 2 and ends in quadrant 1. This is the same for all exponential functions, so it's really important that you put that this is decreasing. So because it starts exponentially high to infinity and then goes towards x, it goes down, it's increasing. The domain, it can go left and right forever, so x such that x is an element of the real number set. And the range, because it cannot be below the x-axis, it has to be bigger than x-axis. We know that y such that y is greater than 0 for the element of the real numbers. And it can't be equal to 0 because then it would be on the x-axis. And the number of turning points is none. You don't have any turning points for a quadratic. It either goes down forever or up forever. So for the other one, we have no x-intercepts. Our y-intercept is at 3. Our end behavior again goes from quadrant 2 to quadrant 1. But this one goes up, so it is increasing. Domain is x such that x is an element of the real numbers, and the range is the same as well, y such that y is greater than 0 for the element of the real numbers. And there are no turning points.